surfaces.
I apologize, I forgot to record.
Yeah.
Yeah, so when you're asked to graph a surface in my class, I'm not going to make you do like crazy stuff. I do want you to just be able to identify a cylindrical and sketch that, and that's with one variable missing. And then the quadrics have a very special format to them. Does that
Okay.
help it answer your question or?
Yeah. I understand now.
Yeah. Yeah, but I want you to get there's infinity different surfaces out there, but no way am I going to ask you to graph all the like the one I just graphed for
Range.
fun for you was it was just for fun. Yeah.
Yeah.
Yeah. Just to apprise you of the fact that there's going to be many different kinds of surfaces out there and for you to be aware that there's infinity possibilities. That's all.
Yeah. Okay. I get you.
Okay. So I'm going to close this out. And let's go to vector valued functions. Vector valued functions. All right, so we are done with chapter 13. Congratulations. That's basically the first module of this course. To recap chapter 13 in 25 words or less, here's what I expect you to get from it. Fun and play with vectors, how to deal with vectors, add them, subtract them, cross product, dot product, projections, all that good stuff, okay, with vectors. Then what? And then we did a little bit of surfaces like plane equations, and the sphere equation, so that kind of thing. And then we just did the cylindrical and quadric surfaces, so you should be knowing that. And then we also looked at lines in space and how to uh, basically define a line in space, which is parametric equations. And that's basically it. And there's a little bit extra thrown in there, but so you should know how to do stuff in chapter 13 now. And I know that you're probably still working on that, but that's fine. So now we're going to start the next module of the course, which is chapter 14. And in chapter 14, we're going to take our knowledge of vectors and kind of put them on steroids. We're going to look at a new kind of function right now called vector valued functions, which are cool. And we're going to do some fun and play with vector valued functions in this chapter. Okay, that's basically this chapter. All right, so let's hit it. So we're going to look at vector valued functions. What is it? So we're going to look at something, plane curves, which we've done a little bit, and space curves. Oh, what about that? Well, we already did a space curve because that's a line in space, but that's not a curve. Well, the vocabulary in this class is kind of a little bit maddening sometimes. The word curve could mean any type of thing in space that like a line or something. It could be squiggly or curvy, sure. Um, so curve is sort of a misnomer. So let's do the two definitions, one for 2D and one for 3D. So in 2 dimensions, a plane curve will be described by a set of parametric equations, essentially, where your x can be found by some function of t and your y is given by some other function of t. And I claim you already studied this. You did this in calculus 2. Really? I don't remember. You did. You did. Well, when did you do it? Probably the last week of class when you studied parametric equations. Does anybody remember that from calculus 2? I'll check the go
Fortunately,
vote for
yes.
me. Go vote for me on the yes, no, and the reactions. Go click on yes or no. I'll check it. Yes, you remember, or no, can't recall. Okay, click on yes or no in the reactions dash there. 2, remember, anybody? I'm looking. You guys remember parametric equations? Like if I had a quick pop quiz right now on parametric equations, would you remember what to do?
Oh wait,
Not
no,
really for
parametric.
me.
Now I see it. The minute that you said that, it hit me like a train.
Yeah, yeah. Again, they probably did it the very last week of class. I start running out of time and I cover it pretty fast when I do Calc 2. And I
No,
tell the students,
like
this has nothing to do with sequences or series that we just finished, but you're going to need it for Calc 3. And they're like, everybody's dead, by that time. Okay, nobody's voting here. So are you guys alive?
Yeah, yeah, I just don't have that reaction.
Okay.
Yeah, neither do I.
All right. So we are going to do reviews, so don't worry. I'm not going to pop quiz you on that. Don't worry. All right. So I claim you already did this, but, you know, and we'll do a little bit of review. Now, a space curve is just going to be the set of all ordered triples where you're going to have functions of t for x, y, and z. That's all. And we already did one of these. We did one of these where you had a set of parametric equations, y, for a line in space. A line in space is defined by a set of parametric equations, x equals something, y equals something, and z equals something. Although it's not just anything, they have to be linear. Because remember, a line in space looks like this set of parametric equations. You guys remember? You're going to have a quiz on it this weekend, so I hope you remember. Okay. So we're going to introduce a new type of function right now, a vector valued function. So this type of function maps real numbers to vectors, okay? So before I do the block diagram, let's go with a quick review. Something that you're already supposed to know. Really? Well, yeah, when you did functions back in an algebra class, say y equals f of x, what do you feed the function and what is the output? So when you feed the function, and this is a function of a single variable here, when you feed the function a value, say x, is that thing that you feed it a point, a real number, or a vector?
A real number?
Yeah, you feed it a real number. Very good. So, you know, like x equals 2. What is the output? Is it a point, a real number, or a vector?
A real number?
It's also a real number. Good. So you feed it a real number and it poops out a real number. Fine. Now, I was trying to trick you to see if anybody fell into my trap, but you didn't. Congratulations. When you put these two things together and create an ordered pair out of it, the input and the output together, that helps you graph the curve. Yeah. This helps you graph it. But that's not one of the inputs or the outputs. So now let's look at this new function over here, vector valued function. So I'll do a 2D, but you can jack this up to a 3D. You're going to feed it something, and it's going to output something. What you feed it is t. T is going to be a real number, some real number, like, and usually t represents time, but not always. But vector valued functions are commonly used to represent motion of some object, you know, over time. And t typically, and t is called the parameter, it's typically time, but not always. Now your vector valued function, because it's a vector, see how this is boldface? So when you denote it on one of your quizzes, please use vector notation like this. And it's going to equal, angular brackets, some function of t for the x component and some function of t for the y component. And it's gonna poop out a vector. So the output is going to be a vector, like the vector AB with constant scalar components. Now, this is the 2D version. There is a 3D version also. So if I'll just put that here, you're just going to jack it up with an extra dimension here. So you'd have f of t, g of t, h of t. And then the vector that you would poop out would be a 3-dimensional vector. That's all. Okay, so now let's do the official definition here, and here in this definition, instead of component notation like I like, they're doing the IJ notation, the linear combination of your standard unit vectors. That's fine. Either way, that's a vector valued function. So I like component form, but some people don't. So, you know, pick your poison. So it's a function. Now, just like any function that you studied in your pre-calculus course or your calculus course, we're going to do the same study. Since we're introducing it, we're going to talk briefly about graphing it, then we're going to talk about domains, and then we're going to do limits today, like today for reals. Next week, I'm going to teach you how to take derivatives of these vector valued functions, and then we'll also do integrals of these vector valued functions. We'll do calculus on it. Yeah. So Vector valued functions serve dual roles in the representation of curves. If you let the parameter t represent time, you can use a vector valued function to represent motion. Yeah. So you can trace the graph of a curve. Now, when you graph one of these vector valued functions, full disclosure, for reals, you're actually getting a collection of the outputs, which are just vectors. But you're never going to see the graphs look like a collection of vectors. What happens when somebody wants you to graph one of these vector valued functions is you won't graph all the vectors. What happens is the vectors get erased and just the tips of the vectors get connected. It's like connecting the dots. So you only see the curve itself, the tips of the vectors getting shown in your graph. And similarly for a 3D vector valued function, the real graph should be, a collection of vectors, because that's what the outputs are. But what we do is we don't graph those, we just connect the tips of those vectors, okay? So there's a curve in space. Now, let's do some review of what you did when you took a Calculus 2 course, or I hope you did. I don't know, maybe you didn't. Maybe you ran out of time. Who knows? So if you have a graphing calculator handy, it would be really awesome if you could whip it out right now and do this along with me so that you have a little bit of experience graphing vector valued functions, okay? So if you were to graph letter A, where your vector valued function has components t squared and t cubed, how would you do that? Well, you could do it by hand. And the way you would do it by hand is you would make 3 columns, one for time, where time would run both negative and positive, like -2 seconds, -1 seconds. And then you'd have 1 column for the x and another one for the y. And then you would simply graph these points. So you would graph the point with coordinates 4, -8. Oops, that's a 1. And this would be -1, and so on and so forth. So you could do this in slow motion, basically, by graphing all of these points in the second and third columns. But I would rather us do it on the graphing calculator because it's quicker. So how do you do it? You first have to go into mode and make sure that you're in parametric mode. Right now I'm in function mode, so I need to move my cursor down and change my mode to parametric, hit enter, quit out of this, and then go to y equals, and you'll notice I have x1 of t, y1 of t. So the x1 of t would be for us t squared, and the y equation is t cubed. And then don't hit graph yet. Go into your window and make sure you're getting the full picture, because if you don't get the full picture, I won't give you full credit. So let's say I left the t minimum as 0 seconds, and let's make the t maximum 10 seconds. What happens when I graph where I'm only looking at the range of t minimum 0 and t maximum 10? I claim I only get half the picture. Now let me do a Zoom Z standard for a second here. What happens if I change the range? So if I have my range be more inclusive to -10 seconds as the minimum and 10 seconds as the max, I'm going to get the full picture. And so there it is. And the other thing that's missing from this graph is an orientation. So the big difference between graphing curves here and graphing things that you graphed, say, in an algebra course, is that parametric equations graphs have an orientation. So this orientation, you need to put an arrow on the graph, just one arrow, to show me the direction it got sketched out. So this arrow indicates orientation. And without it, I can't give you full credit. So we're done with letter A. Now let's graph letter B using your graphing calculator. So if I go back here, I want to make sure, since I'm graphing trig, I better make sure that I'm in, my radians mode. I am in radians mode. That's good. So I'm going to go here. I'm going to clear out these guys, and let's see what happens when my x equation is cos t and my y equation is sine t. Now, when you're doing trig, typically you only need your range to be between 0 and 2 pi or 0 to pi or something like that. You usually don't need like -10 to +10 typically. But it does depend on the graph. So I have to be careful saying that all the time. So here, if I go 0 as my minimum and 2 pi as my maximum, and I graph it, I will get the full picture. That looks like an oval, but that's only because of the way your screen displays. It's really a, let me do z square here so you can see. It's really a circle centered at the origin of radius 1. So that's the true graph. So if I go like this, and it was sketched out in the counterclockwise direction. So let me put a little arrow there indicating counterclockwise. What happens if you were graphing this parametric equation where your x equation is sine, but your y is cos? What's the difference between letter B and letter C graphs?
You'd be going clockwise.
Correct. Yeah, this one is, the graph looks the same, except the orientation is different. And that's the big difference between the two graphs. This guy was sketched out in the clockwise direction. So I put a little arrow on there to indicate clockwise. Okay, now let's do something else you were supposed to have done in your Calc 2 course. Not only graph, but eliminate the parameter. What the heck? Eliminate the parameter means you're going to get rid of the t is the parameter, and give an equation, a single equation that's rectangular that has only x's and y's in it. Only x's and y's, because you got rid of the t. And that rectangular equation has to match the parametric equation. So let's do letter D first. Let's take a look first at graphing it. So if I go and clear out these babies and graph t squared minus 1, t squared minus 1, and then t, and let's check my window. I probably want -10 to +10 seconds as my range. I get a sideways parabola. It's sketched out pretty quick. Did anybody notice what direction it got sketched out at? That was pretty fast.
No, I wasn't able to see it as well.
Yeah, you can't blank. It was that way. Now, how do you eliminate the parameter? This one's super easy. First, what I do is I write down the two equations where I have x equals and y equals. That's how I start. Then I look at the two equations. I go, hey, which one of these is the easiest to solve for t? And it turns out this one's already solved for t, like t is equal to y. So it's like, I don't even have to do any work for this one. Ah, nice. And then you plug in that t into the other equation. So x is equal to y squared minus 1 is the single rectangular equation. And it turns out that is exactly what the graph of x equals y squared minus 1 looks like. Yay, success. And we're done with letter D. So how would you do the same thing for letter E? Well, let's graph letter E first, just to see what he looks like. So if I go back to y equals and clear out these babies, my x equation is square root of t. And my y equation is 3 minus t. And don't blink because you want to see the direction this thing gets. Let me check my window. -10 to +10. Yeah. Hit it. Whoa. And it looks like it's just half of a parabola. And it looked like it was going down. So it was like this. All right. There it is. Fine. So how do you eliminate the parameter? Well, before I do that, how do I get this x-intercept? Anybody have any ideas to get the exact x-intercept? You guys know that an x-intercept has y equals 0, right? Because that's how you have an x-intercept. So what you do is you take your y component and you set it equal to 0. Okay, fine. And then what? You solve for time t. So t is equal to 3 seconds when we are intersecting the x-axis. But that's not the answer. That's not the x-intercept. Don't go, oh yeah, the x-intercept is 3. No, 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 no. That's what time it is on your watch when the object crosses the x-axis. So you're going to substitute 3 seconds into the x equation, and there's your x-intercept, square root of 3, okay? That's how you get an x-intercept. Okay, now how do we get the rectangular equation? Once again, the way I start is I write down my two parametric equations, x equals and y equals, and then I go, which one of those looks like it might be easiest to solve for t? And the best answer for this one, believe it or not, is this. So I'm going to square both sides, and I get that t is equal to x squared. And then I substitute that into the other equation. So y equals 3 minus x squared is the rectangular equation. But there's a problem with this answer. I won't give you full credit. Why not? Because y equals 3 minus x squared, if you were to graph that on your graphing calculator, that gives you the entire parabola. And we want only half the parabola. So we need to erase the left-hand side of our parabola. So the way that we're going to do that is we do what's called restricting the domain. And the domain here, in order for these graphs to match, would be as long as we make sure that x is always positive or greater than or equal to 0, rather, then it will only be graphing that right-hand side of the parabola. And so the final answer is y equals 3 minus x squared, comma, the restriction of the domain x greater than or equal to 0. And we're done with that one. Let's look at another one. And this is another Calc 2 problem. I give this to my Calc 2 people. Graph this and then eliminate the parameter. So go back to your graphing calculator and go, okay, what the heck does 3 cos and 4 sine look like? Don't forget you needed to give an orientation. So this is 3 cos t. And the y is 4 sine, fine. And I think all I need when I do a window for this is 0 to 2 pi. So I'm going to just do 0 to 2 pi and hit it. Whoa, and that is an ellipse. Notice that the x-intercepts are 3 and -3, and the y-intercepts are 4 and -4. And it looked like it's sketched out in the counterclockwise direction. So let me graph those intercepts real quick. And then, whoa, well, that is a sad looking ellipse. Sorry. Well, you get the idea, huh? It's Friday. Okay, if I eliminate the parameter for this one's different. The technique is you don't solve for t. Watch closely. So here, when I see trig, that means in order to eliminate the parameter, I'm going to use an identity. The identity is cos squared theta plus sine squared theta equals 1. I'm sure you've seen that identity sometime in a trig class as well as a calculus course. Well, how is that going to help me eliminate the parameter? I'm still going to start by writing through my x and y guys out. But then instead of trying to solve for t for either of them, because that's going to give me a nightmare like arc cos and arc sine, I don't want that. What I do is I solve for cos t, not t. And in this one, I solve for sine t, not t. And then I take these coses and sines and plug them into my trig identity. So what I'm going to get when I eliminate the parameter is x over 3 squared plus y over 4 squared is equal to 1. And then you can clean this up a little bit by actually doing the squaring. And I hope you can identify this as a standard equation of an ellipse. You probably saw that equation in pre-calc, and that is an ellipse. And so the graphs match, so we're good. And then the last one I want to do for you, I do this for my Calc 2 students and it freaks them out. So I thought I would do it for you. This one is kind of cool because it's like weird. So if you go to your y equals and graph this, you've got t squared minus 2 is the first, oops, not plus, sorry, minus. And then the y component is 2 minus t squared. Fun. Now, first what I'm going to do for you is I'm going to have the window be 0 to 10, just to show you something weird. When I have the t minimum be 0 seconds and t max be positive 10, I get a line. It probably drew it so fast you didn't see what was going on there. But I claim it was going the downward direction. And if I do the window going from -10 to 0 instead, it goes to the left. It goes up and to the left. So it goes both directions. What? Can you do that? Yeah. This is a really interesting curve because it goes this way and then it comes back. It's like makes a U-turn. But it doesn't go, it's a really weird line because it stops here. Now, where does it stop? And it turns out it stops when time t is equal to 0 seconds. So if you plug time t equals 0 seconds into your vector valued function, you'll get -2, 2. And that point right there happens to have coordinates -2, 2. So this is a kind of cool curve. So how would you eliminate the parameter? This technique is a little bit different from what I did before. I'm not going to solve for t. I'm noticing that t squared shows up in both of those components. I'm going to make it easy on myself, and I'll solve for t squared instead. So if I solve for t squared with the first parametric equation, I get t squared equals x plus 2. And then if I substitute this in place of the t squared for the y component, and keep in mind I will have to distribute that negative, I'll get y equals 2 minus x minus 2, but the 2's cancel and I get y equals -x. Now, here's the problem though. That is a single rectangular equation because we eliminated the parameter, but the graph of y equals -x is an entire line. It's the entire diagonal line, and I don't want the entire diagonal line. I only want this part of it where, you know, it's cut basically. So I have to do a comma. And I say, as long as x is greater than or equal to -2, I'm restricting the domain. Now the graph will match the graph of the vector valued function when I add this extra restriction on his domain. And I'm done with that. Now we're going to do something else. We're going to go backwards. And this is key in Calc 3. Now, the problem with me teaching you this right now, early in the semester, we're only in week 3, is that this skill will not be needed until like May. So unfortunately, I'll go over it right now, but I claim you'll probably forget it when I'm going to go, hey guys, remember when we were parameterizing way back? And you'll go, no. And I'm going to go, that's what I thought. Sorry. Bummer.
Yeah, that's gonna.
You know, this is the times where, I wish that I had what's called a photographic memory. My dad actually has a photographic memory, which is really annoying because like pretty much almost anything that he reads, like he'll remember. Like he'll remember the author of a book he read 5 years ago. And I'll go, what? I can't even remember the title of the book I read. One time I was talking to him because I took, as an electrical engineering major many years ago, I took this, it's called a power engineering course. Very cool. You learn about motors and different kinds of motors, and your lab, you get to work with motors, which is really cool. And that's another story. I almost got electrocuted. Ask me about it during office hours. So I forgot everything in that class. Like if you ask me anything about motors right now, I would go, I got to go. I'd have to read it all over again. So my dad was talking to me over dinner. This is like 5 or 10 years ago. Oh, do you remember, the DC motors and the 3-phase motors? And I'm like, no, Dad, no. And he remembers all the stuff he learned in college. It's crazy. Photographic memory. All right. So how do you parameterize? So this is going backwards. What did we do just now? These last few examples, you were given a vector valued function and you had to eliminate the parameter and come up with a single rectangular equation. What if I give you the rectangular equation and I go, ooh, I want you to give me the vector valued function? That's called parameterizing. So we're going to parameterize. That is, give a vector valued function that has the parameter. Now, folks, I'm going to make this as easy as possible for you. I'm going to give you 3 rules of thumb, depending on the case. Case 1, what if you have a function of x? I claim y equals x cubed plus 1 is a function of x, okay? Fine. So what you'll do is your answer is going to be some v of t equals, you got to have your vector valued stuff, some question mark, comma, question mark. I don't know, well, that's has your final answer has to look like. Well, if it's a function of x, good news, it's super easy. Just let x be t. Seriously, folks, just let x be t. It's that easy. Then what? Well, since y is equal to x cubed plus 1, your y component, if you just substitute x equals t, will just be, in this case, t cubed plus 1, and you're done. And to check your answer, on your graphing calculator, when you're in function mode, graph the cubing function x cubed plus 1, and then compare it with the graph of this vector valued function. I promise you they'll be the same. So that's rule of thumb number 1. Second rule of thumb, what if you have a function of y instead of a function of x? And somebody said, come up with a vector valued function. No problem. Since you have a function of y, what you'll do is you'll let y simply be equal to the t. Okay, there he is. And then you do substitution again. You substitute a t in place of y. So the x component will simply be t squared minus 4. And we're done. Congratulations, you just came up with the corresponding vector valued function. It's that easy. There's no catch. Really? It's that easy? No kidding. Now, the last one is a little bit tricky because this is neither a function of x or y. Well, how do you know? Well, if you graph it, it wouldn't pass a vertical or a horizontal line test. And that's a circle of radius 4 centered at the origin. So when that happens, you got to come up with some, hopefully, some trig identity to help you out. You know, we're going to use a trig identity. We're going to use cos squared theta plus sine squared theta equals 1. That's going to be the trig identity that will help us parameterize this equation. Well, what do you mean? First, I'm going to divide both sides by 16 because I need it to look like this trig identity equation. And after I divide both sides by 16, I do have a 1 on the right-hand side, which is good because this 1 matches the 1 on the right-hand side of my trig identity. Oh, so what? Now I rewrite this as a sum of squares. X over 4 and y over 4. And then I'm noticing if I'm going to make these two equations match, because that's my plan, then cos theta has to be equal to x over 4, and you'll solve that for x, and x is 4 cos theta. And then the sine theta has to match y over 4. So you let y equal, after solving for y is equal to 4 sine theta. And then I claim, ba-boom, you now have a vector valued function. The parameter is theta, but you can just as easily substitute t for theta. I don't care. I'll just use theta is fine as a parameter. You can use it. And so your final answer would be, here is a lovely vector valued function that matches the rectangular equation.
Oh, I know this.
What's that?
Isn't this r cosine theta and r sine theta?
Very
That's
similar.
the for the
Yeah,
Cartesian?
but yeah, similar to that. Yeah. I don't want to get into polar right now.
Okay.
Don't go there because it may or may not help you now. We will be doing polar this semester, so yes. Okay, so I'm done with that. That is a quick lesson on parameterization, which is basically you're given a rectangular equation and they want you to come up with a vector valued function for it. Fine. Now, this is not a trick question, folks. This next question here, what would the sketch of the curve look like if your vector valued function was that? I claim you studied this in 13.5 already. I'll give you a hint. The x looks like 2 plus t, right? And the y is 3 minus 4t. And the z is negative 1 minus t. Does that set of parametric equations remind you of anything?
The 2-point thing.
I don't know what a 2-point thing is.
Where it's like,
The parametric equations of a line.
Thank you.
yeah,
Very
yeah,
good.
that.
Yeah, it's parametric
see.
equations for a line. So the graph, the sketch of the curve is going to be a line. So these are parametric equations for a line. And so the final answer is, if you had to sketch this curve, it would just be a straight line. So graph is a curve, well, a straight line curve, because this describes a line in space. Yay! And we're done. Okay, I'm officially done with the intro to vector valued functions. And I claim it really is parametric equations on steroids, essentially, where you take your parametric equations and you basically jam them into a vector valued function notation. That's it. Now let's do a little bit extra on these brand new functions. Let's find out what the domains should be or can be. This is similar to finding domains in your algebra or pre-calc class. All of the same rules apply when you are finding domains. Let's say you were asked to find the domain of y equals 1 over x. You guys remember this? This is like all real numbers except what? What would be not okay to feed this function y equals x, 1 over x?
0.
Yeah, except x equals 0. So you wouldn't want x to equal 0 because, you know, division by 0 is considered bad. So you guys know how to find domains for regular functions of a single variable, I hope, because you did that. So we're just going to jack it up on steroids now. All of those same rules apply, except you're now going to have to worry about satisfying all of the components of your vector valued function. And that means you're going to have to take the intersection of sets. So first of all, here's all the rules that I go over when I teach pre-calc. First, I assume all the inputs are okay, and I assume t can be any real number. But then I start worrying if I see certain things happening. So do I see any denominators that might have a variable in it? Because if that's the case, I might then have to worry about division by 0 and have to eliminate any values of t that would be making the denominator 0, because we don't want to divide by 0 still. Then I have to look at, hey, are there any square roots? We're going to avoid complex numbers in this course. So you don't want to have the possibility of taking square root of a negative number in this course. You may have to eliminate any values of t that would make that square root have a negative radicand. Okay. What's another thing that we worry about when we're looking at finding domains? When you're taking ln of something like ln of x, in our case ln of t, or maybe ln of t minus 1 or something, you need the argument of these logarithms to be purely positive, because you can't take ln of 0 and you cannot take ln of a negative number because you'll get into trouble. Okay, and then of course arc cos and arc sine, those arguments are limited to the range -1 to 1 inclusive. So that's another issue. And then finally, you're going to have to intersect all the individual domain sets. So what the heck am I saying? Let's do some examples. We'll start off easy and then we'll get hard. And this is, by the way, this stuff should be pretty basic for you because you saw doing domains in an algebra class and your pre-calc class. So it's not something crazy. The difference is going to be you have to know how to intersect sets. And that's where I see students flunk this. So I'll go over why that's the case. So first you do each thing individually. If you just look at LNT, what is his domain? Well, you need the t to be greater than 0. That has to be true. Otherwise that component won't be happy. So the second component, the t, there's no restrictions. He could eat everything. He would have all real numbers. So all reals. The last component, we got problems. You got to worry. Well, what do you got to worry about? Well, you need the radicand to be greater than or equal to 0. That has to be true. And then if I rewrite this inequality a little bit better by adding t to both sides, I get that t has to be less than or equal to 1. And now you intersect these 3 sets. So what are the values of t time t that make all 3 of these sets happy? Now, if you're having trouble, what I do, and I'm not trying to insult your intelligence, I do color graphs. So for example, for t greater than I draw 3 number lines like this, and I line them up so the 0 is, vertically aligned. What would, if I had to graph t greater than 0, that would mean I'd put an open bubble on the 0 and I'd shade in all of the values of t, these are t number lines here, to the right. What about the no restrictions? Well, if I had to graph his domain, all reals means I would shade in everything. He can eat any real number in the world. Fine. Oops. Then what? Sorry, let me go to undo. Then the last guy, I'll use a different color because I'm trying to make a point here. When I'm going to graph t less than or equal to 1, I color this bubble in because 1 is included in the set, and less than means I shade in all the numbers to the left. Now, if you can collapse all three of these number lines into one big number line, what values of t would take on all three colors? What values of t would be blue and red and pink? Bluish, reddish, pinkish. I don't know, that color might be weird color. That would be the intersection. And I hope that you get that the answer is going to be values of t that do not include the 0, because that's an open bubble, but will include the 1. And so your final answer is t is an element of this very small range. And that's the answer in interval notation to letter A. And that means that that vector valued function can only eat numbers between 0 and 1, where 1's included and 0 isn't. Questions?
So is this the only method, or are we going to being taught like another alternate or quicker
No,
method to do
this
it?
is the only method I know of.
Okay.
This intersection part is where students can't do it. They go, oh, I know how to do each of these individually like you did. I'm like, great. But I don't really give you any partial credit for that, because that's something that any self-respecting pre-calc person could do. Can you intersect all three sets? And a lot of students can't. I don't know why. I give you this little color number line and condense all the number lines into one little technique. I invented that technique. I've never seen it anywhere. It just works for me. But if you have another technique of yourself where you know of how you're going to intersect sets, go for it. Whatever works for you. But you have to make a clear argument for me, you know, on your paper of why it works, right? So I'll go ahead.
What does that say for T? The no ver.
I don't
For
know
all,
where
right?
you're looking.
I think it
For
mentions
the
the
T
for all
dot dot.
symbol.
This is an epsilon, which is a Greek letter, and it means belongs to. Is that
Is
what
that-
you're asking about?
No, like above the square root of 1 minus T, where you drew it.
Right here, or this guy right here?
No, to the left.
Right here?
It's the one where you've circled it in blue. The
Well,
T.
I have a lot of things circled in blue, Nathaniel. Can somebody help me out? Does anybody
I
know
think
what
you mean-
Nathaniel's asking? Otherwise, I need to take it on offline because I'm really in a hurry today. I'm
Is it
sorry.
no restriction?
The no restrictions? No restrictions, all reals, Nathaniel? Is that what you're looking at?
Yeah.
Okay,
Yeah,
that says no restrictions on his domain because he doesn't have any restrictions. He can eat anything.
Okay.
He can eat all reals.
Yeah,
I'm gonna
sorry
move
about
on. I gotta move on.
Yeah.
This one, I'm gonna do this one real
Got it.
quick. Does this have any, if this were just e to the t has no restrictions on his domain. Okay, but that's not what this is. This is e to the 1 over t. So you do have to worry because the 1 over t has a denominator that has a variable in it. So that means t can't equal 0. How about cos cube root t minus 2? Well, cube roots don't have any restrictions. You can take, it's legal to take cube root of a negative number. So this second component, Nathaniel, I'm writing no restrictions here, but very quickly. That means he can eat all real numbers. And then this one, you do have to worry because you don't want the denominator to equal 0. Why not? Because denominator equals 0 is bad. That would be horrible. So here's how I tackle that. I first set the denominator equal to 0. I know we don't really want that to happen. And then whatever solutions to this quadratic equation that I end up getting, I'll actually delete those from the domain. So we're solving this quadratic equation in order to figure out what values will make the denominator 0. And then we'll go, oh, we don't want those. Okay, does anybody know how to factor a trinomial? You may have something called the diamond method or whatever. But whatever method you use, I really hope you know how to factor trinomials. Oh, my view just changed. Sorry. I don't know why it does that. For no reason, it's got a ghost. So I'm gonna, because I'm really strapped for time today, really bad, I'm going to just tell you what the fact, you could use the quadratic formula, okay? That's always an option. If you like the quadratic formula, sure, it works anytime you're solving a quadratic equation, go for it. I claim if it does factor, it's a little easier to factor and then apply what's known as the zero product property. So it turns out that this has a factorization, and then if something times something equals 0, the ZPP, the zero product property, says when you have a product equaling 0, you're allowed to set each of the individual factors equal to 0. That's how you solve it. And then when I solve it, I get two solutions, and you have to be careful. These are not the answer. This is what's not okay. So I'm going to put not and like not equal. We don't want these numbers because they're bad. Why are they bad?
Because the denominator gets to 0.
Yeah, they're going to make that denominator yucky. So now it's time to intersect the sets. So I'm going to do the number line thing. So if I draw, this is the way I intersect sets. If you have a better way, God bless, please go use it. I'm going to line up my number lines. This is the t-axis 3 times in a row. The first component, e to the 1 over t, remember, he can eat all numbers except for the t equaling 0. So I'll put an open bubble around the 0, and I'll shade in all the numbers to the left, and I'll shade in all the numbers to the right. Those are okay. The second component didn't have any restrictions. He can eat anything. He's allowed to eat the entire real number line. So I'm just going to shade in everything, all reals. The last component, which we just did, we can eat everything except for -1/4. So I'll put an open bubble on the -1/4, and +3/2. Put an open bubble there. But he can eat anything else. So I'm going to shade in all the numbers between -1/4 and 3/2, oops, as well as anything less than -1/4. And this PDF annotate doesn't like it when I do straight lines. And shade in everything to the right of the 3/2. The green is everything he's allowed to eat, okay? Now, in your mind, can you imagine collapsing all 3 of these number lines into one number line? What values of t would be red, pink, and green at the same time? This is kind of hard.
Is it -infinity to the -1/4 with parentheses?
Good.
And then is it unions?
Union. Very good. Union with a big U.
And -1/4 to 0, both with parentheses.
Good. Union.
Union. And then 0 to 3/2.
Mm-hmm.
Union. And then union 3/2 to infinity.
Very good. That would be the final answer. That's a domain. That's the intersection of all 3 sets. Those are the values of t that would be pinkish, reddish, greenish, all at the same time. I don't know if you can imagine that for yourselves, but I hope. Okay, in about 15, 20 minutes flat, I'm going to do limits. Oh, I'm going to take it on, baby. That's how I roll. So I'm going to do a limit review, and then we're going to do limit problems. Do you remember L'Hopital's rule? I hope so.
Yep.
So first up, I'm going to do the definition of a limit of a vector valued function. It's really easy. You're going to laugh. It's great. And then we're going to do a limit review, and I'm going to whoosh it through quick because I know a lot of people forgot their limit facts. And then we're going to do some limit examples, and then we're out of here. Okay. But first, let's take a poll because I want to see if you're still here. Okay. So what do we got here? Let's do a phobias poll. This is good. Do you have any phobias? Rodents, snakes, spiders, all of them, heights? No, fearless me. Go. Yeah, funny, huh? Okay. Are we voting here? All right, I'm going to end the poll. So I hope everybody voted. Here we go. Wow, looks like a lot of you are afraid of heights. Good to know, huh? Good to know. Some of you spiders. That's a pretty common fear, heights. So I would say you're normal. Okay, let's do the definition of a limit, shall we? So there's the reason why there's two definitions here. One is for 2D and the other one's for 3D, but it's basically the same. So it's so easy, please. If somebody gives you a vector valued function and says, hey, take the limit of a vector valued function, all you have to do is the answer is also going to be a vector value. It's going to be a vector, essentially, a scalar vector. You're going to just take the limit of the first component and take the limit of the second component and then put it all together in a vector and you're done. Same thing for 3D. That's all you need. So that's it. This is calculus, baby. And here's what you're doing graphically. So if you do have L being the vector that's the limit, and when you take the limit of your vector valued function as t approaches some number, here's your R of t, this vector here basically approaches 0. Okay, so they're showing you a picture. So let's do some limit facts. Does anybody know what 0? Oh, my internet's unstable. Sorry. I have no idea why. Okay, does anybody remember what 0 divided by 2 equals? This is easy. Don't make it hard.
0.
Yeah.
0.
How about infinity divided by 2, for example?
Infinity.
It's still infinity. Beautiful. Now we're going to do 2 that have to do with the ln. I'll graph ln of x if that makes it easier for you. So if x approaches infinity, then you're basically looking at what is ln infinity.
Still infinity, no?
Yeah, it blows up. How about ln of 0 from the right? So when x gets really close to 0 from the right, what does this graph do? I'm giving you a hint here.
Negative infinity.
Negative infinity. Very good. ln of 0 is essentially negative infinity. Please know these. This should be cold, people. You should know these cold. But I'm going over them for your benefit, not mine. How about 1 divided by infinity? What's 1 divided by a very large number? Yeah, 0. Very good. Now, the next 2 have to do with e to the x. You know, what's e to the negative infinity? Or if you looked at the graph of e to the x, what's the limit of e to the x as x approaches negative infinity? That way.
Negative.
Is it 0 or negative infinity?
It's 0. It's 0. E to the negative infinity is 0. If you didn't learn this in Calc 2, I'm here to tell you. You better know it cold. And so what if your base is something other than e, like, 5? 5 to the negative infinity is also 0. Okay, how about e to the positive infinity?
Infinity.
What happens when it blows up. Okay. E to the positive infinity is infinity. Know these limit facts. How about 1 over 0? Normally you would say like, oh, that does not exist. It's undefined, right? But in Calc 2, they probably taught you that it was infinity. And if you didn't learn that, you did now. And then negative 1 over 0 is negative infinity. Okay. Cos of infinity. Well, if you look at cos, because it oscillates between 1 and negative 1, and so does sine, the limit does not exist as x goes to infinity for either cosine x or sine of x. Okay. Just because of the nature of the beast. It just goes oscillating up and down forever and ever. It never settles down. However, if you were taking the limit of a cosine or a sine, in the numerator and the denominator goes to infinity. So here, yeah, plus or minus 1, okay, it doesn't exist. But the denominator is growing very, very large, then the limit does exist and it's 0. Okay, now let's look at arctan. Real quick, you should know your arctan facts because I'm really into arctan in this class. You may have forgotten what the graph looks like, so I'm here to remind you that it's kind of cool. It has 2 horizontal asymptotes, like that. And the this upper horizontal asymptote has the equation y equals pi halves. And the other horizontal asymptote is y equals negative pi halves. Okay, fine. So what's the limit of arctan as x goes to positive infinity? Well, what is this graph getting closer and closer to?
Pi over
This
2.
dotted line, which has the equation. Yeah. And how about when x goes to negative infinity?
Negative pi over 2.
Yep. Very good. And now we're done. Well, wait, I have a few more. Sorry. These. 0 divided by infinity, that's 0. Infinity divided by 0, infinity. 0 to the infinity, 0. 0 to the negative infinity, infinity. Infinity plus infinity, big number. Minus infinity, minus infinity, minus infinity. Now careful, because 0 to the 0 is indeterminate. And infinity minus infinity is indeterminate. You probably learned that in Calc 2, okay? We're not going to run too much into those indeterminates in this class, so you're safe. Let's do some problems, and L'Hopital's rule may be needed, may or may not be needed. So rule number 1, anytime somebody asks me to evaluate a limit, you know what I do as step 1? What do you do as step 1?
And put the limit into the equations.
Yeah, and that's called direct substitution. Thank you, Hannah. You got it. So, and that should always be your step 1, because if it's not on your handwritten work this weekend, oh boy, I'm going to take off so many points. Your head is going to spin. And you'll go, oh, I got the right answer. And I'm going to go, that's nice, but I didn't see step 1. Well, I did it on a piece of scratch paper. Okay, so what do I mean by direct substitution? Here they're saying t approaches 1, and here's a vector valued function. So first up, direct sub. You go, what's 1 squared plus 1 minus 2 over 1 minus 1, ln of 2 minus 1, cos of 3 pi times 1, like that. Because that might actually give you answers. Like you may not have to do much work. You're like, hey, this is easy. Now, the first one, 1 plus 1 minus 2, I get 0 over 0. This is indeterminate. So we're going to have to do L'Hopital's rule on this one. We got more work to do. The second component gives us ln of 1. ln of 1 is a nice number. Does anybody know what that is? It's called 0. How about cos of 3 pi?
Is that -1?
Yeah. Now, this first component, you're going to need some work because 0 over 0, don't tell me that's 0. Oh dear. No, that's not okay. Using L'Hopital, you're still going to take the limit as t approaches 1, but I'm going to take the derivative of the numerator. So I get 2t plus 1. And divide that by the derivative of the denominator. So the derivative of t minus 1 is 1. And then do direct sub. Try it again. Okay. What do I get here? Ooh, I get a nice answer, 3. So what is our final answer for letter A? The limit does exist. And the answer is this lovely vector. It's a constant vector. Constant vector because it's got nice constant components in it. Any questions on letter A? This is an introduction to limits of vector valued functions. Not too hard. Okay, we'll move on. Letter B, check out this baby. I'm going to do each of these components separately just because that's usually how I like to work. So if I am taking the limit as t approaches 0 of this first component, I first use direct sub, sine of 0 minus 0 over 0 cubed. Oh dear, what is that going to be? That looks like 0 over 0, which is indeterminate. So what does that mean? Well, that 0 over 0 means I'm allowed to use L'Hopital, so let's go use it. So LH is how I denote L'Hopital's for short. So you're still going to take a limit as t approaches 0, but I'm going to take the derivative of the numerator. The derivative of sine t is cos t minus the derivative of t, that's 1. And I'll divide that by the derivative of the denominator. So the derivative of t cubed, 3t squared. Now let's try direct substitution. What do we get here? I think cosine of 0 is 1, people. I get 0 over 0. Uh-oh, that's indeterminate. Again, can I use L'Hopital's another time? Sure.
Yeah.
So LH again, use it as many times as you need to. Lather, rinse, repeat. Okay, now we're going to take the derivative of the new numerator. The derivative of cos t minus 1, I believe, is negative sine t. Divide that by the derivative of 3t squared. I get 6t. Oh no, are you kidding me? I get 0 over 0 again. Gosh darn it. Let's use L'Hopital's again. Oh, how many times does it take? As many times as you need. So the limit as t approaches 0 again, only this time you're taking the derivative of minus sine t, which is minus cos. Okay. Woo! And now what? Then divide by derivative of 6t, which is 6. Now let's hope I get an answer here that is not indeterminate, and I get negative 1/6. Ooh, finally. Okay, so the first component has a limit, and it's negative 1/6. Now, how about the second component? So if you work on the second component, 3t over t minus 1, using direct substitution here, I get 0 all over 0 minus 1, but that's 0 divided by negative 1. Can I use L'Hopital's?
No.
No, you're done. What's 0 divided by negative 1? It's a nice number.
0.
0. Right. Okay, keep going. So what about arctan e to the t squared over 2t squared? What I do is I first look at the e to the t squared over 2t squared. I take that separately. I find his limit as t goes to 0. And so what you're going to get is e to the 0 over 0, which is 1 over 0, which is infinity. So then what? Well, then you plug that into your arctan. So what is arctan of infinity equal to? Check your limit facts that I just gave you.
Pi
Pi
over
over
2.
Pi halves. So the answer for the third component is pi halves. Fabulous. Then what? Take these three answers and shove them into a vector, because your final answer has to be a vector. I better not see pure numbers just sitting there. If I don't see your final answer as a vector, I'm going to have a conversation with you. Okay. And so the final answer for that guy is that limit, that vector. Okay. Finally, let's just do this real quick. I got 2 minutes. I got to use it. If you're going to take a limit now at infinity, I love limits at infinity. Here, when you use direct substitution, you plug in the infinity, I get e to the negative infinity. Check your limit facts. That actually has a limit. What does e to the negative infinity equal?
0.
You betcha. Then let's take the limit as t goes to infinity of the second component. Now, when you plug in infinity into these little polynomials, you're going to get negative infinity squared minus 2 all over 3 times infinity squared plus 5. And it's like, well, what the hell? And it's going to turn out where the numerator is just negative infinity, because whatever. And then you have divided by positive infinity. This is indeterminate. And you're totally allowed to use L'Hopital's. I'm not going to. I'm going to show you the quick and dirty way to do this problem. By the way, L'Hopital's will totally work. But I want to remind you of something you learned in Calc 2. Let's apply growth rates. So if you remember something in Calc 2 called growth rates, if you have a polynomial divided by a polynomial and you compare the degrees of the polynomial, in this case, the degrees are a match because both of the polynomials are a degree 2, the second degree in the numerator and a second degree in the denominator. So what does that mean?
The limit is negative 1/3.
Yeah, exactly. The degrees match, and you just take the leading coefficient over the leading coefficient. Your limit exists, and it's the lead coefficient over the lead coefficient. So boom, we're done. All right. And then finally, the last guy is asking you to take a limit of t squared over ln t. And if you use direct substitution, you're going to get infinity squared over ln of infinity, but that's basically a big number over a big number, which is indeterminate. You can go ahead and use L'Hopital's rule. You might have to use it more than once and you'll get an answer. But I'm going to do growth rates. So let's apply growth rates. Let's see if you remember your growth rates. Who goes to infinity fastest? Polynomials or logarithms? They both go to infinity as t goes to infinity, but one of those goes to infinity so much faster than the other, it's almost like the other guy was standing still. Does anybody remember?
I think it was ln. No, it was the exponent.
Polynomials grow bigger than logarithms. They grow faster. If you forgot that, go use L'Hopital's, okay? But because polynomials go faster, the numerator goes to infinity so much faster than the denominator, this whole thing is basically going to blow up. It's going to blow out. Well, then what's the answer to letter C? Well, even though the first two components had answers, the final answer is the limit does not exist because the last component blew out to infinity, thereby making the entire thing blow out. And we're done. Congratulations, you're now officially done with section 14.1. I'll stay for a couple of minutes